Welcome to Approximately Correct.
Hey, Marlos.
Nice to have you here. You are an assistant professor at the University of Alberta in computing science. You are also an Amy Fellow, and you hold a Canada CFAR AI chair. We're so excited to have you here with us today to talk about your research.
That's true. Thank you for having me here. I'm very excited to be here.
Did you want to talk a little bit about what you work on in general?
Yeah, so I like to say that I work in AI in general because I think it's drawing these boundaries about like, oh, I work in a specific technique or something like this. It's sometimes silly. Knowledge is much more universal than that, and I like to think about how we can use knowledge from other areas. But at the end of the day, if I'm supposed to be put in a box, I would say that most of what I do is reinforcement learning. It's this notion of learning by interacting with the environment, learning how to achieve goals by interacting with the environment. And in a sense, it's very similar to how we learn, right? Like we try stuff out and we see what works out, what it doesn't, and we go on from there.
We did want to talk to you today about using RL in the real world.
Yeah.
So you've recently worked on a project which I found fascinating. I've heard you talk about it a few times, involving balloons.
Oh, yeah.
So could you tell us a little bit about what you were doing there?
Yeah, so during my PhD, I did a lot of work on like fundamental reinforcement learning. I was evaluating a lot of my ideas in video games, right? And then when I finished my PhD, I saw this opportunity. I joined Google, and I saw this opportunity of like, they had this project that was just starting about flying balloons in the stratosphere. So those balloons, they were from the Loon company. It was a subsidiary that Alphabet had, that basically the idea was that they wanted to provide internet to people. And the way that we provide internet to people is that we have an antenna, right? Like, so here we put an antenna in the downtown Edmonton. So now this antenna is going to have a diameter of 5 kilometers of range. And because of that, there's a huge area that is covered. So there's a lot of a big chunk of our population that gets the signal from that antenna. But now imagine that you want to provide internet to a tribe in the Amazon forest.
Right.
Well, maybe you have a dozen people in that tribe, and you don't have anything nearby in the next 5 kilometers. So what they're going to do, they're going to build an antenna there.
Yeah, probably don't want to bulldoze the Amazon to put up like a...
We don't even know how to get there to build an antenna. It's kind of hard, logistically speaking, but even if we do, economically speaking, it wouldn't be great.
Yeah.
So, but you know what would be great? If we could build an antenna that was 40 kilometers long, because then the range is going to be much bigger.
I see.
But we also don't know how to build an antenna that is that tall. So because of that, what was their idea? The idea was like, let's station a balloon. And the balloon operates as the antenna.
So you just kind of put it on the balloon and send it up that...
Exactly. So the balloon is going to be the one, like you have a station downtown that it's, downtown. You have a station on the ground that it's sending the signal to the balloon, and the balloon is kind of like serving as the antenna.
Mm-hmm. Okay.
That was the idea. The catch, of course, is that those balloons, they need to stay where they are, and there are winds coming from all sorts of directions. So the Loon, they were already providing internet to some people in Kenya, for example, and other places, from what I recall. But basically, the idea was that they had this solution that was derived from basic principles of engineering, how to station the balloon. And when they approached the researchers at Google, it's just like, do you think you can do better?
Right.
And that was the challenge that we took upon us. It was just like, can we do better with reinforcement learning? We decided to approach it as a reinforcement learning problem. Can we do it better with reinforcement learning than what we can if we have some very, very smart people working on this problem for 3 years and coming up with a closed form solution from first principles of engineering? So that was the whole motivation for the project in a sense.
Okay. And how did things turn out?
They turned out great. It's
good to hear.
It's almost too good to be true, in a sense that it's just like, we went from starting on work on the project, and of course, I don't want to be dismissive of all the hard engineering work that the folks at Loon had already done to give us a simulator, to give everything that took years to develop. Mm-hmm. But when we started the project, we were in a pretty good shape, because we went from the project to submitting the paper. It took us a year or so it's relatively quick to do the whole thing. But basically what happened was that we wanted this balloon, basically the way we would say is that, like, there's this range, this area that we want the balloon to be inside. So we would say, well, basically in reinforcement learning, we reinforce good behavior. So we give a cookie to the balloon every time that the balloon is inside the region. And And basically, we trained the balloon to do this. And what we were able to do at the end was to show that the balloon was not only on the region more often than before, but it was also more power efficient.
Okay.
So it was a multi-objective optimization problem because we're trying to, like, of course, we can try to be as often as we can in the region, but these balloons are solar powered. So we want to make sure that we're also being mindful of the energy that they're consuming. And we got the best of two worlds in a sense, so it was pretty good. And it's funny because it's a really difficult problem. And one of the things that I think we always struggle to do is to convey how hard of a problem it was.
Yeah.
Because basically you have the balloon and the balloon is not propelled. So what we need to do is basically we put the balloon up there and now the winds are going to blow the balloon one direction or the other. And then all you can do to make sure that you're in a region is just like, oh, there is a wind blowing the balloon in this direction, so the balloon is going to go down a little bit because maybe there is a wind blowing it in this direction. And then like you keep doing these patterns. So it's not that you just stay there and there are no winds and you're good, you know, like.
Or also, I didn't know it wasn't propelled.
It's not propelled, right? Like, because, So based on that, we were just having to ride the winds and.
It's like a sailboat.
It's literally that. So like, and we do see like when we look at the trajectories, and this is in the paper, we even see the tacking behavior that you see like in boats that like, I want to go to that direction, but there is no wind taking me there. So I'm going to go in the diagonal and eventually I'm going to tack and do it and keep doing like the zigzag or something like this.
And was that like a surprise? Was that something that you were expecting to see?
Well, the tacking behavior was the first validation that we had that we were doing something right.
Right. Yeah.
Right. Like when we deployed the balloon the first time, and we saw the tacking behavior, we did not even know if it was better or worse than the engineers. Like, oh, it's learning something.
Yeah.
You know, but and the important thing is that like in real world applications, those things matter, right? Like, and basically we were able to provide, if I recall correctly, almost 1.5 hours extra hours of internet a day to people in Kenya because our solution was more effective. So like we were inside the region actually providing internet, and there are some gorgeous behaviors that were learned. One of the things that surprised me the most was that after everything was said and done, we had deployed 15 balloons in the Pacific Ocean for 3 months to do A/B testing to see if like, okay, is our solution actually better than the engineering one and so on. We did all that. And then we were looking at the data, just like, okay, so now let's be scientific about it. The Loon folks are absolutely sure, like this is the best solution. We can deploy it. It's already better. We like that gut feeling that you get after spending multiple years watching those things. Yeah. But we're like, no, let's try to quantify this. We wanted to write a paper at the end, after all. And one behavior that we noticed was that, again, the balloon is solar powered. And what would happen is that consistently at the end of the day, let's call it the balloons that were controlled by reinforcement learning, they would go to a lower altitude than the balloons that were just engineering-based ones. And we were looking at this, it was like, well, this seems to be a consistent pattern, but we can't explain why.
Yeah, like why would that be?
So we went to the engineers and said, like, well, and they're like, this is brilliant, because what the balloon actually learned to do was that they're solar powered. And the way that these balloons operate is that they have a fixed volume. So once they are there, if you want the balloon to go down and they have a fixed volume, what do? You pump air into the fixed volume, and now the balloon is going to become denser and it's going to sink. And if you want the balloon to go up, you're just going to open the valve, the air comes out, same volume, it's lighter, it goes up, right? So that's how the balloon works in the same way that submarines work. And based on that, what happens is that they're solar powered, and this is how they operate. Pumping air into the balloon costs energy. Opening a valve and letting the air out doesn't. So now what did the balloon realize? If I go to the bottom of the altitude that I can, that it's not going to be really bad. Let's say all things considered, I'm going to go as low as I can. When the sun sets, if a bad wind comes up, I can just open the valve and I can scan the whole altitude that I'm allowed for free. I don't take any energy. So putting it shortly, the balloon learned to store potential energy by just interacting with the world and realizing that feels better. You know, like it's as if you're going atop of a hill and realize that, well, I can just let it go because I'm going to go downhill if I want, like on a slide, and this is not good. So by just interacting with the world, the balloon realized that that's what made sense in terms of the energy efficient. So I thought it was pretty cool.
So it was learning to kind of prepare for the future.
Yeah, exactly. Yeah.
So we talk a lot about challenges when implementing RL in the real world. And I can't think of a more challenging atmosphere than, I guess, the atmosphere? Like, I mean, it's like you talked about energy. You can't just plug in a
Oh yeah.
40-kilometer extension cord. So what other challenges did you have to face dealing in this particular environment?
One of the things that happened is just like when I'm talking about playing Atari games, for example, right? If you look at the neural network that I was using to play that Atari game, the neural network itself was bigger than, it wouldn't run in an Atari console. So in a sense, the brain, quote unquote, of my agent was bigger than the whole world that it had to interact with, right? But now when you go to the real world, like, we don't know how to predict the winds. Like, in fact, papers were written about this, that the model that we're using to try to get some resemblance of accuracy of the winds, sometimes it was 90 degrees wrong. But now think about it. We want to go this direction. We think that the wind is going this direction. And when we get there, the wind is here.
Yeah.
I was like, so how do we deal with all this uncertainty, all the complexity of the world that, like, it's hopeless to expect our agent to actually be able to run? This was a big challenge. Another one that it's quite common, and people write a lot of papers about this, is what people call sim to real, right? Like, we train things in simulation, but then we deploy them in the real world. And it was always a very interesting conversation to have with the engineers, because they would approach us and we would say, okay, so how often are we taking actions? How often are we decide to go up, down? Like, oh no, it's 3 minutes. Okay, cool. So 3 minutes in the simulator, that's what it does. So then we go to the real world. How often are we taking these actions? It depends. Like, wait, what? I thought it was 3 minutes. Well, yeah, best case scenario, it's going to be 3 minutes, but sometimes we don't have a signal. Sometimes it's 4 minutes. Sometimes, how do we expect this to work? Like, this is not what we trained this balloon to do, you know? So there are all those things that happen, and sometimes they're just hilarious. Like, one of the things that just showed the gap between simulation and the real world is that at the height of our arrogance as AI researchers, thinking that we could solve everyone else's problems, they gave us the simulator and said, okay, that's it, go figure it out. 1 week later, we come back and say, 2 weeks later, we come back and say, we solved your problem. Here's 100% accuracy. And then the engineers look at us like, of course you didn't. Like, no, we did. Look, your number is still giving us 100%. Yeah. Like, it's impossible. The winds are not that friendly. It's impossible. Sometimes there is no wind in your favor, so you cannot be inside the region the whole time. But the numbers say that we did. So let's look at the numbers. You know what the balloon learned to do? The balloon learned in the simulation that you're going to the center of the region it was supposed to go and go up, 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 up. At the moment that you leave the Earth's atmosphere, you pop because of the difference in pressure. You go down and you're inside the region forever. So 100% accuracy. But that's not really intended, you know. Like, so after we had a couple of interactions like this, we make the joke that eventually they took the training wheels out, and they're like, oh, that's the real problem that we actually have to deal with. But yeah, so there are many things that we have to deal with.
Yeah, the real world has a way of not cooperating with exactly what you were planning.
Yes, exactly. And it's also interesting how quite often we don't understand how the nuance of the problem, because you're saying like, oh, nothing is as hard as like the atmosphere and like the real world. And that's true because of all the complexities of the weather and so on. But at the same time, it was a very benign problem for us to work on, in the sense that we didn't have anything else around us, right? Like, so we were flying above the height that the airplanes fly. So it's not that we're freaking out about, oh, what if there is a pedestrian crossing the road? Or like, so we were learning about those things, but it was a very safe environment, because of course safety was always a top concern for us. And I remember that they're telling us that there was one time that there was an alert at the station about like, oh, there are 2 balloons flying really close to each other, and we almost had a collision. And then we went to see, it's like, oh yeah, because they were flying 5 kilometers past each other, and that was like almost a collision.
So you trained in a simulation, and then when the balloons were in the sky, were they still learning?
No. That's a very natural question that people ask, and I think that it highlights one of the weaknesses of the field in general. Yeah. And that's something that I really care about, and that I spend a lot of my time thinking about, because the balloons were not learning. And in a sense, we didn't know how to make it learn. That's the point. Like, the reason is just like, everyone is like, yeah, just let it learn. And then everyone's like, we don't trust. And, you know, like, we trust our solution right now. We don't trust let it learn, you know, like, and it was bizarre, because we should. because we are deploying this in 15, 20 balloons, dozens and dozens of balloons, and each balloon is different. Each balloon is slightly different because maybe a balloon is older and the battery doesn't hold as much charge as it would before. And we never actually learned the nuance of any of those things. We had a standard model and we're deploying and it worked fine. But I feel that there was so much more to gain if we were learning online and adapting to the nuances of each balloon. But we don't know how to do that in a sense. And it's like, I make the joke that it's just like, it's fantastic. I find it mind-blowing that we just put a balloon in the stratosphere with reinforcement learning, and the balloon, without ever being told physics, learn how to store potential energy to be more power efficient. It's just like, oh my God, this is amazing. But at the same time, they came to us not only with a simulator, they had years and years of data about balloon flights. We got those reams of data and we put in the garbage can. Like, we don't know how to use the data, and we don't know how to learn online. We can deploy this, so I feel that there is still a lot to be done in that sense.
Yeah. Now, you said you didn't trust trying that online learning. Like, what do you mean? What was the concern in your mind?
Well, one of the concerns is that will the behavior degenerate? Right? There is a field of continual learning or continual reinforcement learning. And one of the things that by now it's a very well documented phenomenon, we wrote a paper last year about this in DeepRL, is the notion of what we call loss of plasticity, for example. Okay. So what happens is that I'm going to learn how to do something, and it's amazing. Let's say I'm going to learn how to play an Atari game, and I'm going to spend a lot of time learning how to play that Atari game. It's amazing. It's superhuman. Who cares about how well I can play an Atari game? But it's superhuman. Great. Okay, so now what happens if I ask you to play another game with that same agent?
A different game.
A different game with that same agent. And at first, we're bad because the whole world that you knew was that other game. But you're going to learn how to do well if you give it enough time. Let's say, okay, so now let's go to the first game again. What would you expect to happen? Maybe my brain is very limited and I can only learn how to play a game, so I'm going to start bad again, but I'm going to go up. Right. And what we have shown, and many other people in the field have shown, is that you cannot go as high as you went the first time.
Oh.
You are losing your ability to learn.
Because you learned something else.
Well, I mean, the word because is dangerous because we're going to attribute causation to a phenomenon that we don't necessarily fully understand yet. But it's just a notion of and as we keep going over and over again, as we do it for longer and longer, eventually these neural networks, they just lose more and more plasticity. They lose more and more their ability to learn to the point that eventually it's just a flat line. It's just I can't do anything.
So to bring it back to the real world, this would be like a person learns how to ride a bike. They ride the bike in the summer. In the winter, they ski. They come back to ride the bike in the summer, and it takes them a while to get ready. A person would get as good as they were last year at the bike, but an RL agent would never get as good as it was last year on the bike. Wow. Then it would go to the skis, and it would not be as good as, and eventually it can't do either.
Exactly. Yeah. And you know what's the most bizarre thing? You know how we solve the problem from an RL perspective, from a machine learning perspective for that person that learned how to learn how to ride the bike? You lobotomize that person. And now it's starting fresh.
Right. It's better to forget everything.
It's better to forget everything. So my group has been doing a lot of work on trying to understand some of the underlying phenomena that is going on, what causes it, or what are the things that we can see as predictors of this thing going on. But this is just one of the concerns, right? We call it machine learning. And we got very used to the idea that we're going to train a system, it's going to learn, and we're going to deploy a fixed system into the world.
It does one thing.
It does one thing.
Yeah.
It's interesting because we call it learning algorithms, but they are learned. Right. They're not learning anymore.
Right.
Yeah.
Right. So when you talk about continual learning, it's kind of a weird thing to say because it should actually be called learning. It's the only thing that it's actually learning. The other things were learned. So a couple of years later, it became much more common to talk about continual learning, but basically it was fairly obvious to us that it's just it was not the wisest thing to do, to just let it run. There's another aspect that was particular to the balloons themselves, which is the fact that still to this day, the reality is that our reinforcement learning algorithms, they require a lot of samples to learn. Right. They require a lot of data, a lot of experience. And in a sense, it does make sense. If I don't tell you anything about the problem, and I've just said, hey, figure out how to live in this world, and in a sense, you do not even have parents to to raise you, you will have to try a bunch of stuff, and you're going to say, oh, I think this matters, but oh, I was wrong, and I have to do it again. So, but it does take a lot of time. We can accelerate that time when we're doing simulation, right? In the real world, if we were to think about the lifetime of a balloon over a year, and like, oh, look, we have a year worth of data for a balloon. That's nothing in terms of what we needed. So it's not about necessarily only continual learning, but then there are interesting questions about what we call fine tune, can we adapt the behavior just with like that additional data? So we had a lot of conversations about, okay, now once we have put a man on the moon, how do we do it better? You know, like that's the moment that we, for all sorts of reasons, different people moved to different places and we stopped working on the project.
On this loss of plasticity thing, it seems really like strange and almost mysterious. Do we know why? Like, do we have any thoughts on that?
We have noticed, for example, that loss of plasticity happens way quicker when you have tasks that are very different from each other that you're seeing.
So if it was like skateboarding and snowboarding.
Exactly. So maybe it would at least take longer for you to observe that.
Yeah.
Right.
In more technical terms, the change in distribution really matters. The distributions that the tasks are coming from, or the similarity between the tasks. There is something to be said that is just like, do we even really have tasks? Like, or is it not like a slowly changing thing that like, it's not that one day we snap our fingers and everything is cold and like there is no, you're going to realize, wait, this is slippery and maybe I can slowly adapt to this, to skiing before I'm riding my bike. But this seems to be one factor. Another thing that we have seen is that when we have neural networks, quite often, not always, but quite often, we have what we say that the outputs saturate, basically a bunch of dead neurons, things like it doesn't matter what you do, they're just going to output 0 all the time. So in a sense, you're losing your ability to reactivate that neuron. I have a PhD student, Alex, who has been doing a lot of great work on this. And one of the things that he noticed is that basically you look at all this, papers and papers have been written about explanations. Let's try to explain what this is going on. And what he did was just say, okay, let's try to be consistent here. Let's go through all these explanations and let's try to find a counterexample. Because if I find a counterexample, it means that that explanation is not sufficient. Right. It doesn't mean that it's necessarily wrong, but it's not sufficient because there's something that it's not capturing. And he observed this correlation that what seems to happen is that as you keep moving forward over like this progression of tasks, the way that we train these neural networks is that basically you have a gradient that you're trying to minimize. So think about like a 3D surface that you're just going to throw a ball at it. It's just going to go downhill. Right. So basically, you're going to go downhill trying to get to that minimum. And every now and then, it's as if you change the shape of the surface, right? Like some of the ball is going to go a different path. And what he has shown, and all the data seems to suggest that this is true, is that the metric that we can quantify that is predictive of loss of plasticity is what we're calling loss of curvature. Is that every time that you're changing that surface, it's becoming flatter and flatter. And if you have a surface that it's completely flat, the ball is not going to move anywhere.
Right.
We want to make sure that we have diversity of gradients. We want to make sure that we have all these directions that the gradients can go. And we consistently observe that every time that we observe the loss of plasticity, a little bit before the loss of plasticity, or at the same time, or a little bit after, we would see this loss of curvature. It's a correlational explanation. We can't attribute causation. The reviewers don't like that. They really want us to attribute causation, which I find hilarious. It's just my rant. It's as if you're telling Galileo that what you did is not worth it because you haven't told me why two objects fall at the same speed, even if they have different mass. Like, give it 100 years, Newton will figure it out. But I'm still excited about the fact that like the correlational observation is the first time that we have some consistent, at least for now, and that's how science works, right? Like maybe this week someone is going to put a paper out saying like, oh, look, this is a counterexample where this doesn't work. Right. But it's this notion that like, we're losing this ability to learn because it seems that we're basically just losing dimensions that we can navigate to try to learn. So that seems to be one of at least it's the running hypothesis in my lab at this point.
So how can you introduce diversity of gradient? Like, what does that mean?
I mean, it's the boring answer from the 80s in machine learning. We can do regularization. Okay. So, for example, one thing that we do is that we know that if we lobotomize someone, they can learn. I mean, don't try this at home. But if we were to start our network from scratch, it could learn. So now, can we try to learn how to minimize that objective while also ensuring that we are going to end up in a distribution that is similar to the initial decision? Because that's the regularizer. So we say, like, now we have two objectives. It's not only to minimize this, but it's also to make sure that we have this diversity of gradients. So like, can we make it in a way that the distribution of weights that I'm going to converge to is going to be similar to the distribution of weights of the initialization? Because if you have that same distribution, then you have the diversity.
Yeah. Okay, so it seems like there's lots of problems with this continual learning setting. Are we just like out of luck? Is there anything we can do to fix?
I don't think that we are out of luck. I think that there is a matter of focus. For the longest time in machine learning, the focus has been about deployed models, right? Like learning something and then deploying that fixed model, fixed evaluation, and so on. So we have to recognize that there are decades of research that were done in that setting. And then when we start doing continual learning, we imported all that research and we're going to apply there. And in that sense, what we have been shown, what my lab has been shown, is that the standard solutions from those systems, they don't necessarily work that well. I like to talk about how every time that we need to solve a sequential decision-making problem, like reinforcement learning problems, we have to do three things. We have to do credit assignments, we have to do exploration, and we have to do generalization. So what are those? In credit assignment is that, let's say we're playing chess, and I win the game. It's very unusual that I win the game because of my last move. Right. It's probably something that I did 10, 15 moves before that gave me an advantage, but then I still had to bring it home and win the game, you know, right. And we are pretty good at knowing that, oh, the reason that I won the game was that winning move, you know, like that was the winning move. So I can assign credits and this was important. So that's one thing that we always need to do. The other one is exploration, which is how do I win the game in first time, right? Like if I always go to a restaurant and I always order the same food, how can I learn that there is something better than the one that I'm going to do? So I have to try things out, to see new things. And if you think about learning, you have to try things out to realize that, oh, this is a possibility, and then I can assign credit to that thing. But then what happens at the end is that if we think about complex problems, like flying balloons in the stratosphere, we're never going to see the same wind configuration that we saw the day before. So we also have to generalize, right? Like I kind of know that the pattern of your shirt doesn't really matter for our conversation, right? Like I can walk past that. And we also have to see that, like, oh, these things matter, these things don't matter, and they're same. And we always have to do those three things. And the problem is that how do we deal with those in standard machine learning? Well, credit assignment, we were basically just training a neural network, but I just told you about loss of plasticity, right? Yeah. Exploration, we have a lot of theoretical results showing that, yes, you're going to count the number of times that you've seen different things, and we can have a confidence bound, and we're going to shrink that confidence bound, and then I'm very sure about how good this is, and I'm going to then explore to a different place. But when the world changes, what do those counts even mean? Yeah. You know, like
it was a lot less relevant.
Another approach for exploration is like, oh, every time that I see something that looks novel, that looks different, I'm going to go after that thing. But now if everything looks novel because the world just changed, you know, like what you're going to do. So we have written a paper showing that all those techniques fail when we're going to do continual learning. The problem is changing. But then, of course, there are ways that we can try to address this. And generalization is also the same thing. The generalization boils down to what we call the representation that we learn. So like we're going to have a neural network, we're going to then train that neural network, and somewhere in the middle, it's going to abstract away some things and say like, oh, these two things are close together in the neural network land, these are far apart. And what we also showed is that the standard representations that people use, they are not necessarily the best for continual learning. So in a sense, we have to revisit the fundamentals of what we think is right to do continual learning. But I don't think that the things look bad. In a sense, they look exciting because there is research to be done. You know, like, and I personally have a favorite thing that I think it's the way to go, which is the notion of abstractions. And we can talk about abstractions in both state and time. And what do I mean by that? We don't have to do abstractions in terms of the observations that we have, right? Like I have to be able to abstract away that maybe these things don't matter, those things really matter. We have to talk about that, but then we also have to talk about something that it's quite, like people who have read the fundamental papers, they know about those things, but it's not that it's the mainstream of the papers that are being published, which is this notion of temporal abstraction. Because when I tell you that, like, if I were to ask you, like, how am I drinking coffee? I'm not going to say, I'm going to move my hand a little bit further and further and further, and then I'm going to twitch my muscle like that. Like, okay, we're going to be very bored really quickly. And I describing that to you, it's not even going to be useful because probably I cannot even replicate that myself, and you definitely can't. But instead, if I tell you, like, I'm going to grab the mug, and I'm going to bring it close to me, and I'm going to then sip the coffee, that's an abstraction, right? Like, because when I talk about it, like, I'm abstracting this whole movement into a sequence, like a sequence of muscle twitches. I just abstracting, like grabbing, and then doing the next thing and so on. So there is this, but the language that we generally use for reinforcement learning when we were talking about the balloons is just like going up, going down, going up and going down. We actually started, one of the things that I did that I'm excited about in that balloon project, I started to sneak in some of those ideas in the project, because just like, think about how do we explore when we were flying these balloons. When we explore is that we're going to come and say, okay, I'm doing this and this looks really good, but maybe I should try something else. I'll go up. Okay, I'll go stay here. It looks really good. And maybe I'm going to go down. And then you just like you're D3 in the same place. And if you think about a 20-kilometer range, you're going up for 3 minutes in the balloon. It's not going to change much, you know, like. And the exploration strategy that we used when we were training those balloons is that every now and then the balloon's like, okay, I'm going to explore. And what I'm going to do is that I'm going to see what the winds look like 10 kilometers above me. And that meant that maybe the balloon was going to be for an extended period of time going up in a very purposeful behavior to get to that place, like, I'm going to explore. So the balloon was using a temporal abstraction to the exploration, you know?
Sorry, what's the temporal abstraction?
The temporal abstraction would be the balloon choosing to say, I'm going to go up 10 kilometers above me. That's not 3 minutes. That's not an action. It's a sequence of actions that would take
over and over again.
Exactly.
Okay.
I think that the notion of abstractions, and like at the moment that we have an abstraction, it's also much easier to talk about generalization, right? Like, how do I drink coffee? Well, I grab this. How do I drink tea? Oh my God, I've never seen tea in my life. It's probably the same thing, you know, like I can abstract those things away. We can think about them. Sometimes they use this word as skills. We acquire skills that can be then reused in other places, right?
Yeah.
And now let's talk about how do we assign credit. Did I let this fall because the muscle twitch that I had at the very first time, or because I didn't grab the handle properly?
Maybe you have to find the right part in the process.
Right.
But if you have the abstractions, it's much easier to look over these chunks than to talk about the millions of muscle twitches that I had, you know, like. So I think that there is an exciting aspect, because when we look at standard reinforcement learning problems, abstractions don't really pay off. Because mainly temporal abstractions, because why am I going to spend the time learning abstractions on how to play an Atari game if at the end of the day I can literally time all my actions to be as precise as possible? Like, I want it to be as fine-tuned as possible. But now if you embrace the fact that the world is going to be extremely complex, then you need abstractions, because you're going to have to give up the optimality of something to be able to navigate, right? Like, you're not waking up every day like, how can I get to my kitchen as fast as possible? Or like, oh, you know, like, because that doesn't pay off, right? Like, we have a limited capacity of what you think about.
Right.
And I think that that's where abstractions start to, mainly temporal abstractions, start to pay off. But the interesting aspect of it is just like, and the fundamental question that is the one that keeps me up at night, that I like to make the joke, is like, where do abstractions come from? So I have two young kids, and I remember when my daughter was, I don't even remember what she was doing, but she just expressed a behavior that was clearly an abstraction for the first time. And then I looked at her, I was like, can you please tell Daddy how you did that? You would make my life so much easier if you could just explain this, because this comes very natural to us.
Yeah.
Like, what are the abstractions that make sense, that they don't make sense? But we still don't have a very good answer for that.
It'd be difficult to kind of explain those almost intrinsic behaviors that we learn.
Right. Yeah.
Yeah, I mean, that's a big chunk of my research, and that's something that I've been excited about, but I still have to convince the whole world that I'm right.
I'm convinced it makes so much sense to me. Like, that we have in our lives, we don't have the capacity to think through every little action, so we chain them together to create these like higher order things.
Yeah, and the thing that I'm very excited about is this notion of like, but how do we figure out what is the chunk?
Yeah.
You know, like, because I could say that the chunk is going halfway through.
Right.
Why does this, like, oh, but that's really a bad chunk, you know, like, so we are able to do this. And at the same time, if it's a very fine china, we are going to behave different, and we can just adjust, right? Like, and we know that these are the things that we can do and that they are not. So I have this thing that I've been pitching that I've have a lot of people working on this in my group, which is what I call the representation-driven option discovery cycle. So it's a mouthful of words, but like options are just temporal abstractions. And representation-driven is the representation that I was telling you about. So the representation is driving this discovery of temporal abstractions. And the idea is the following. I'm going to interact with the world. And at first, maybe I don't know anything about the world. So maybe I'm going to be random. But eventually, I'm going to do something that is not common. It's something that I realize that I can do by myself, but it's not straightforward to do. The cheesy example that I like to give, and it's a nightmare to do this in front of Alona, but when babies, let's say babies are toddlers, they know how to speak, they're saying a couple of words, and let's say that they learn how to walk. There is an explosion in vocabulary after they learning how to walk. It's a correlational study. It doesn't mean that the walking is what led to the increase in vocabulary, but this is something that has been replicated many times. And if you were to think about this diagram, this cycle that I told you about, it makes sense. And that's the moment that it's my interpretation. It's not what's written in the papers, but it's just like the babies, they are learning how to speak. So they have a way of representing the world. They have those skills. But now let's say that they learn how to walk. They have this new skill. By learning how to walk, they're going to experience things that they wouldn't otherwise, right? Like, how often do I have to tell a baby or that is just like laying on the ground what an outlet is? But at the moment that they're in front of an outlet, that becomes so like
quick.
They experience the world in a way that they were not experiencing that before. So it makes sense that they acquire words, you know, like, so one thing bootstraps the other. So I say that this is a constructive cycle, right? Like, you're always constructing behavior that it's going to serve as a springboard for you to do something more complex. And I think that this is the key to be able to do continual learning, to do increasingly complex tasks while having those skills. And we have, of course, a couple of papers showing this in all sorts of different tasks that this seems promising, at least.
That rings very true for anybody who's had a child go from like infancy to walking, because you have the experience of going places with your kid when they are just like a little lump that can't really move on their own. And then when going places with a kid who can like locomote on their own is just a completely different experience. You have to be so vigilant. You have to be watching the whole time. And so, of course, like, their experiences are very different for the same reason.
Yeah, and I think that, but what makes this conversation difficult is that the way that people are so driven by benchmarks now and try to quantify everything in terms of a number, it's hard to make that type of research flash. And until the moment that we actually have something that is so groundbreaking that everyone is going to pay attention.
Okay. Cool. Yeah, I think that was really far-reaching discussion. We covered the stratosphere, covered babies.
I think we got it all. Like,
yeah, I mean, it just shows that like reinforcement learning, it is really a very holistic framework of thinking about learning, and it can work in a lot of places and take inspiration from a lot of places.
Sometimes reinforcement learning researchers, they sound arrogant because for us it's almost too obvious. Just like, of course you learn by trying things out and interacting with them and seeing what works and what doesn't work. And of course this applies from babies to the stratosphere.
Right.
Yeah, thank you.
Thank you so much, Marlos.
Yeah, thanks for giving us a lot to think about. You helped me with my continual learning today, so I appreciate that.
Yeah, thanks so much for having me here.